We see if the band graph condition is violated for a Jordan arc gamma, then gamma is a straight line interval. It becomes straight. So if gamma is not a straight line interval, that it can be split into parts by the neighborhood maps, and there will be some kind of minimal parts which cannot be diminished, because if there is no minimal parts, if we have some converging sequence of Sin minus 1 Sjn, yes, then we'll get some paradoxes with this. So finally it turns out, if we have a self-similar arc gamma which is not a line, that it can be split into parts, which, if we map them by similarities S1 Sm, they will be mapped inside these parts. And if we have two images of these maps, then they would not intersect. Otherwise, these parts can be diminished more, yes? And this means that a Jordan arc, which is not a line, can be represented as an attractor of some multi-zipper, because it is split into parts, and these parts obey a graph-directed system which is similar to zipper but has several components. So this is a theorem about Jordan arcs. If a Jordan arc is not a straight line, if a self-similar Jordan arc is not a straight line, then it can be represented by some multi-zipper. So this is a very important corollary of this band graph condition. So we need to consider this, how the proof of band graph theorem looks like. There is very interesting proposition which proved in this. I will explain all them one by one. So there are some necessary lemmas which are necessary for formulating and proving band graph theorem. First statement is the following: suppose we have a family of contracting similarities F1, Fm, So suppose S is a system of contracting similarities. I will follow this notation. Yes. And then first statement is the following. The open set condition holds if and only if there is such epsilon more than 0, that for any all incomparable multi-indices this difference is greater than epsilon. For any ST incomparable Fs minus 1 Ft of x minus x if there is x in Rd, Ft minus 1 Fs minus 1 Ft. S and T are multi-indices, minus x is more than epsilon. So this is the first thing which supports this condition. So let us look at this theorem and how it is proved. So if we have the open set condition, then we have the open set V, such that if I and J are incomparable, do you remember what does it mean in incomparable? Two multi-indices are incomparable is one is not a prefix of the other. If they are incomparable, then Fi of V and Fj of V do not intersect, because this is an open set. Yes, the images of open set are disjoint. So I have some problem with remembering words. So they are incomparable. Then if I take some point in V, so this is the open set V, then these images will be disjoint too, right? If we take a point in V, then there is a ball of radius epsilon which lies in V. And let it will be a B. Then Fi of B and Fj of B and Fj, they do not intersect. And what does it mean? It means that Fi of x minus Fj of x is greater than then QI. I don't remember what his he has, yes, let it be QI, is more than QI, some maximum, more than maximum of, or maybe we can write QI plus QJ multiplied by epsilon, because this distance is QI epsilon and they are disjoint. Then if we apply this Fi minus 1, then, or Fj minus 1, so we'll have Fi minus 1 Fj of x minus x will be greater than 1 plus Qi minus 1 Qj. This is a positive number, right? So it will be greater than epsilon, and this is just what we supposed, yes? So we found the point x, right? And we found a distance epsilon for which this inequality fulfills. So if the open set condition is satisfied, then we have it. But we need to prove some others. We need to prove the other side. Oh, other side. Conversely. If the inequality but if it doesn't so if we have open set condition, we have that. But if we have no open set condition, then of course it will not be satisfied. Sorry, maybe we'll make a break now, and then I will continue after. So how large the break should be? Half an hour? Okay. Mm-hmm. 10:30, 10:30, 11. Okay. Okay. Please feel free. And I need to discuss one thing. What? Mike? How can you hear me if I go